Have you ever wondered why the exact same medicine might be a miracle cure for your friend, but for you, it does absolutely nothing? Or even worse, it gives you a ton of nasty side effects? Well, the answer isn't just random chance. It's actually hidden deep inside our bodies in a tiny, microscopic world of chemical processors that literally decide a drug's fate.
To really get why this is so important, let's just start with a number, and it's a big one. $1 billion. That on average is how much it costs to bring just one single new drug from a scientist's bench to your local pharmacy. It's staggering.
So, you have to ask, right? Why is it so unbelievably difficult and expensive? Well, it turns out a huge piece of that puzzle has to do with the wild, unpredictable ways our own bodies react to these new drugs.
And that brings us right to the heart of the matter, the billion-dollar drug problem. It's this massive, fundamental challenge that every single drug company has to face.
You see, thousands of really promising drugs end up failing for two big reasons. First, there's poor bioavailability. That's just a fancy way of saying the drug can't get to where it needs to go in your body to do its job. And second, unexpected toxicity, where the drug ends up doing more harm than good. But here's the kicker. Both of these problems, more often than not, are tied to one single process in our bodies: metabolism. So to really understand what's going on, we have to meet the main characters in this whole drama. Let's call them your body's chemical gatekeepers. They can be the unsung heroes of medicine, or sometimes they can be the villains. They're called cytochrome P450s, or just P450s for short. The easiest way to think about them is like a super sophisticated chemical processing plant that runs 24/7 inside your liver. Their whole job is to grab foreign things, like that pill you just took, and chemically change them so your body can safely get rid of them. And when it comes to this job, they're the absolute champions. I mean, just look at these numbers. P450 enzymes are responsible for a whopping 75% of all drug metabolism in the human body. They are doing almost all of the heavy lifting.
But it gets even crazier. We have 57 different P450 enzymes, but get this, just 5 of them handle about 90% of all the drug-related work. And that one at the top, 3A4, does half the work all by itself. Now, this is actually great news for drug developers because it means they only have to focus on a handful of these enzymes instead of all 57. But, having all your eggs in just a few baskets, well, that can lead to a really big problem. A problem I like to call the metabolism lottery. Which brings us to the billion-dollar question, doesn't it? If these 5 enzymes are so incredibly important, are they at least the same from person to person? Do we all have the same amount, working at the same speed? Oh, not even close. Just look at this. Each one of these bars represents the amount of a P450 enzyme found in a liver sample from a different person. The difference from one person to the next is just wild. Some people are loaded with a certain enzyme, and others have barely any. It is a total genetic lottery. And this lottery has huge, real-world consequences. Check out this graph. That top line shows what happens to a drug's level in the blood of what we call an extensive metabolizer. That's kind of the normal, expected result. But look at that bottom line. That's a poor metabolizer, someone who doesn't have enough of the right enzyme. See how the drug level just keeps going up and up? That's dangerous. So let's just break that down. A poor metabolizer, they're lacking a key P450 enzyme. That means the drug gets cleared out of their body super slowly. So with every dose they take, the drug just builds up and up and up until it can reach toxic levels. Meanwhile, the normal metabolizer clears the drug just like the doctor expects, keeping it in that perfect window where it's both safe and effective. But hold on, there's another twist in the story. Sometimes this whole metabolism process doesn't just fail to clear a drug. Sometimes it can actually turn a perfectly safe drug into a poison. The scientific term for this is bioactivation. Basically, a P450 enzyme tries to do its job and break down a drug, but in the process, it accidentally turns it into a brand new, highly reactive molecule, and that new molecule can be seriously toxic to our cells. So to make this real, let's talk about a drug that pretty much everyone has in their medicine cabinet right now, acetaminophen, which you probably know as Tylenol. When you take acetaminophen, it can go down one of 3 different paths in your body. Now, at a normal dose, 2 of those paths are perfectly safe and handle most of the drug. But that third path, that one's dangerous. And guess who's running it? Yep, our friends, the P450 enzymes. Let's make it simple. Think of it like this. Your body has 2 super efficient express lanes to safely process acetaminophen and get it out. That's what happens most of the time.
But a little bit always sneaks down that third road, the dangerous one, where those P450 enzymes turn it into a toxic substance.
Now, here's the crucial part. At high doses, like in an overdose, those two safe express lanes get completely swamped. They're totally overwhelmed. Suddenly, a huge amount of the drug gets forced down that P450-driven toxic pathway. Your body creates so much of this toxic molecule that it just can't handle it, and it starts attacking and killing your liver cells. That's exactly how an acetaminophen overdose causes such severe liver damage.
Okay, so with all of this, the billion-dollar failures, the genetic lottery of metabolism, and this scary risk of bioactivation, how on earth do we build safer medicines?
Well, the answer is to get way ahead of the problem. Modern drug companies now use something called developability screening. This is a crucial early step where they test potential new drugs against all those key P450 enzymes right there in the lab, long before a drug ever sees a human patient. They're specifically hunting for these metabolic red flags.
And what's the ultimate goal? It's actually pretty clever. They're looking for drugs that aren't dependent on just one single P450 enzyme. The perfect drug candidate is one that can be processed by lots of different enzymes. Why? Because that way, if a patient happens to be a poor metabolizer for one enzyme, the others can just pick up the slack. It's a way to design drugs that can beat the metabolism lottery.
And all of this leads to one final really cool thought about the future. We are getting better and better at understanding our own personal genetics. So just imagine a day when your doctor prescribes a medication that isn't just for your illness, but it's tailored specifically for your body, for your unique personal set of metabolic enzymes. That is the ultimate promise of personalized medicine.